Okay. Welcome. Welcome to season 2 of Astronomy on Tap Bonn. I'm very, very glad to introduce season 2 to you. We're very excited. Last year it was the launch of Astronomy on Tap Bonn, the outreach events which we started here in collaboration with Fiddlers and in collaboration with many astronomers from the Andrei Institute of Astronomy and the Max Planck Institute for Radio Astronomy. And of course, all our speakers from last year. So last year, it was just an idea. I've seen an Astronomy on Tap in Copenhagen at a meeting I went, the Cosmos meeting, and I really liked it. So I said, Fiddlers is perfect for this. And we did it. With Anna, Sandra, Laila, Arti, Toma, I have the names here, Angus, Enrico, who's not here anymore. Angus is not here anymore. We started Astronomy on Tap Bonn, and it was a struggle, but we did it, and we were very, very happy and excited to bring these nights to you. And this year we have more members. We are around 12, 13 people, including volunteers, that prepare this event for you. Anna, Astronomy on Tap. So, this is a small video to show you the team, which includes more people, and we will upgrade the video. And we're here for one mission, as the video says. And the mission is to bring astronomy to the world, to build bridges. And we have a lot of passion, and we like what we do. So this is what we bring to you every month here at Fiddlers. Yeah, of course we're awesome. And we're full of passion, as the video says. We do outreach events outside of Fiddlers. So we did one for the university. We did one in collaboration with Astronomy on Tap New York. And we gave a speech at the United Nations for Climate Change to introduce Astronomy on Tap and how you can use this platform for outreach. And this week, we also have another kind of thing related to Astronomy on Tap. It's Camp for Future. So the students that organize the Future for Fridays for Future, sorry, organize a camp for Climate Week. Yeah, it's the lights. They make my brain liquid. Okay, so it's the Camp for Future, and we're going to give a workshop to the students to educate them on how to use the tools that we use as astronomers to educate the general public for climate change or for whatever reason. We use it to educate them on the advances of astronomy and how it makes your everyday life better. So hopefully they will use these tools for their own benefit. What else? Yeah, this is a team. And thank you very much. I will stop now. I will open the floor to Felix and Anna, if they can join me here, which will present to you the rest of the event. Can we have a round of applause, please? And have a good night and enjoy.
Give it to Felix, he's better. You're duplicating today. Some terrible at this activity.
Just
there. So, hello, good evening, afternoon, evening. We are very happy to have you here, as Eleni said. My name is Anna Mikler. I'm a PhD student at the Andrei Institute, and today I will be hosting the event with Felix.
Ja, guten Abend auch von mir. Ich bin Felix und ich arbeite am Max Planck Institut für Radioastronomie als Doktorand. Und ich mache heute die deutsche Moderation für Astronomy on Tap Bonn. Und wie ihr schon gehört habt, wir werden dieses Jahr 1 Jahr alt. Ja, also macht euch auf ein paar Überraschungen gefasst. Ein paar schöne Preise haben wir. Ja, genau, danke.
So as Felix said, today we are having a lot of special prizes for you. We are celebrating 1 year, although it's our 11th anniversary, but you know, approximations. Just a bit about AOT. We are always here the last Tuesday of every month. We are always happy to have you here, except for the summer. We also deserve a break, so we only do certain events from September to June. And AOT started in New York City as part of an outreach initiative from professional astronomers to tell the audience about astronomy, science in general, to have a space to ask questions, to feel comfortable about it, to just relax, have a pint, and really chat over science. Right now, there are a lot of different teams around the globe, really. We are AOT Bonn, one of the youngest ones, and we are the only team that actually does AOT in 2 languages.
Ja, ein Hoch auf den doppelten Sprachsupport, den wir hier haben. Ja, wie gesagt, Astronomy on Tap wurde 2013 das erste Mal in New York gegründet. Die Astronomen einfach in gemütlicher Atmosphäre, wie in dem Pub hier, einfach ihre Arbeit präsentieren wollten. Und Astronomy on Tap gibt es, wie man auf der Karte hier sieht, jetzt schon ziemlich oft. Und da sieht man auch, wo wir sind auf der Weltkarte. Hier ist es Astronomy on Tap Bonn. Und ja.
If you have any questions, you want to sponsor us, we'll be very happy if you want to sponsor us. You want to participate, give a talk, anything, everything, you can contact us at any social media, YouTube, Instagram, Facebook, not Twitter, not yet at least. But, and you obviously can talk to us directly. There are always astronomers on the audience. Twitter, oh yeah, we do have Twitter. Sorry, I'm just very bad with social media. I had to get Instagram for this, so you know. There are other astronomers on the audience as well, so you know, feel free to bother them. They don't know this, but yes, feel free to bother them. And you know, just any question, come to us.
Genau, uns gibt es auf Facebook, YouTube, Instagram, Twitter, was ihr euch vorstellen könnt. Wir sind eigentlich überall zu finden. Und ihr stellt euch uns auch gern da eure Fragen und folgt uns da, damit ihr auch immer up-to-date bleibt. Und ja, hier im Publikum sind auch ein paar Astronomen. Ich werde natürlich keinen angucken, aber nein, ihr könnt gerne uns oder auch, wenn ihr andere Astronomen im Publikum findet, gerne immer eure Fragen stellen. Und natürlich auch nach den Vorträgen.
As I said, we have a YouTube channel. We do a live stream, so you know, if you're at home watching us, hello. What means is also you can ask questions on the chat. We're happy to answer. We have Laila here who will be paying attention and passing your questions. But that also means that we are streaming at all times the stage. So if you don't want to be on the stream, please do not come to the stage.
Genau, wir haben auch einen Livestream, also hallo an alle da zu Hause. Und ja, ein Gefahrenhinweis, falls ihr nicht auf diesem Livestream erscheinen wollt, dann kommt einfach nicht hier auf die Bühne. Ansonsten, wenn ihr uns im Livestream zuguckt, dann könnt ihr auch uns gerne dort eure Fragen stellen. Wir werden die dann auch beantworten.
Before we go to the first speaker, one little announcement, and is please subscribe in our YouTube channel. If we actually get 100 subscribers, we can put the link beforehand and we can share the live link, and it will help us a lot. And for a year, we've been with 70 subscribers, so we just need 30 more of you. So you know, just go look for us. That'd be great. Want to say that one? No. So our first talk of the day is by Dr. Alan Roy. Felix will be the moderator. And Alan is a staff astronomer at the Max Planck Institute for Radio Astronomy here in Bonn. He led instrumentation development programs with international collaboration in order to image black holes with sufficient sharpness to see the event horizon. So the cool pictures that you actually saw of the black holes, you know, but his job. With a lot of other people, but yes. Before he worked in New Mexico and in India as an astrophysicist. And he also advised for telescope designs in order to look for extra-terrestrial intelligence. Very cool, very diverse. Currently, he's developing solar power stations for the largest and most sensitive radio telescope in the world. And today he will tell us about applications of the solar power plants in radio astronomy.
Also, unser erster Vortrag heute ist auf Deutsch von Dr. Alan Roy. Er ist seit 1999 am Max Planck Institut beschäftigt. Und er hat dort über viele Jahre hinweg in internationaler Zusammenarbeit Empfängersysteme entwickelt. Vor allem auch für die Darstellung von scharfen Bildern vom schwarzen Loch. Und das habt ihr bestimmt auch schon mal gesehen. Das ist auch nur durch solche Techniken möglich. Er hat außerdem, bevor er ins Max Planck Institut hier kam, in New Mexico und auch in Indien in der Astrophysik gearbeitet und auch dort am Design von Teleskopen mitgewirkt. Unter anderem auch das Design für Teleskopen zur Suche nach außerirdischem Leben. Also Er hat wirklich viele Themen berührt und sehr viele spannende Sachen gemacht. Zurzeit entwickelt er neuartiges Empfängerdesign, das die Nutzung von Solarkraftwerken als radioastronomisches Teleskop möglich macht. Damit könnten wir tatsächlich das Abstand größte und empfindlichste Teleskop der Welt bauen. Und damit einen großen Applaus für Dr. Alan Roy.
Danke sehr. Die Geschichte heute Abend hat ihr Anfang eines Nachmittags, als mein Kollege Ivan Camara kam in meinem Büro aus einer Dienstreise in Spanien. Und er machte mir aufmerksam mit einem Bild von dieses Array. Das habe ich nie vorher gesehen. Es ist überwältigend groß. Es besteht aus tausende Einzelspiegel, die die Sonne folgt und fokussiert auf einen Turm in der Mitte. Und es erzeugt Strom tagsüber. Die Frage, die Ivan mir stellte, ist, ob wir das für die Astronomie bei Nacht nutzen könnten, weil beim Nacht liegt alle diese Spiegel unbenutzt. Und wir haben eine kleine Gruppe zusammengestellt. Wir haben schnell erkannt, wenn man das für die Astronomie nutzt, würde man das weltgrößte Teleskop haben. Und ich werde ein bisschen über diese Geschichte erzählen, aber viel mehr über die Astronomie. Warum wir begeistert sind über die Ergebnisse, die Entdeckungen, die man mit diesem Teleskop gewinnen könnte. Es ist schon erkannt in die Radio-Astronomy-Community, dass der nächste logische Schritt in unserer Entdeckungsreise von den letzten 400 Jahren wäre, so ein Teleskop zu bauen, das weltgrößte Radioteleskop. Und ich werde über die Astronomie reden, woher wir kamen in die letzten 400 Jahre, wohin wir gehen und ein bisschen über wie die Solarkraftwerke dazu beitragen könnten. So, das Teleskop ist wie ein Auge. In der Mitte gibt es eine Pupille und das ganze Licht kommt von der Welt durch die Pupille und gibt uns die Informationen über die Welt um uns herum. Die Pupille ist etwa 5 mm im Durchmesser. Das ist ziemlich klein und die ganze Information muss da durchkommen. Wie könnte man das verbessern? Ganz offensichtlich, man könnte das größer machen, aber innerhalb Grenzen. Vielleicht ein Faktor 5 könnte man das vergrößern. Dann brauche ich technische Hilfe hier. Ja, okay. So, Faktor 5 größer. Wir machen das 25 mm Durchmesser. Dann würde plötzlich viel mehr Licht durchkommen in die Sehnerve. Wir würden viel mehr Informationen über die Welt bekommen und wir würden empfindlicher sehen. Wie viel empfindlicher? Ein bisschen Mathematik, das ist die einzige Mathematik heute Abend. Wenn man 25 durch 5 dividiert, hoch 2, bekommt man 25. Das ist die Fläche. Die Empfindlichkeit geht mit der Fläche. So, die große Auge würde 25 mal mehr Licht sammeln als unsere Auge. Und ein Problem dabei ist, man hat dann sehr große Augen und das ist umständlich zu tragen durch die Welt. Aber dieses Problem ist vor 400 Jahren gelöst von Galileo. Er hat die erste Teleskop entworfen. Sein Teleskop hat einen Durchmesser von 25 mm. Und diese Linse, alle Licht, das auf diese Linse fällt, es biegt es und fokussiert es auf 5 mm Durchmesser, damit es durch die Pupille kommt. Und wenn man dieses Teleskop an dem Himmel richtet, das ist wie man Augen mit 25 mm Durchmesser hat. Und er hat das Universum mit seinem Teleskop beobachtet. Und was er sah, hat er aufgeschrieben. Und ich habe ein paar Auszüge hier auf seine Notizen. Er hat unzählig viele mehr Sterne gesehen. Er hat gesehen, dass die Milchstraße aus unzählig vielen Sternen besteht. Und er hat hier kartiert. Das ist in Orion. Das ist die Gürtel und dem Schwert von Orion. Die großen Sterne sind, was man mit dem Auge sieht. Die kleinen Sterne hat kein Mensch vorher gesehen. Mit dem Teleskop hat er unser Universum so viel erweitert. Er hat auch Jupiter beobachtet. Er hat kleine Punktlichter daneben gesehen und er hat kartiert, wie die sich bewegt. Und er erkennt, Jupiter hat Monden wie wir. Er hat den Mond beobachtet und er sah Bergen und Täler wie auf die Erde und er erkennt die Ähnlichkeit. So viel mehr sieht man, wenn man ein Teleskop vergrößert, wenn man das Auge vergrößert. Heute, das ist ein Bild von Chile aus dem Space Shuttle, während der Hubble Space Telescope gestartet war. Und diese Streife ist die Atacama-Wüste. Das ist ein sehr besonderer Ort. Die ganze Wolkenbildung liegt über dem Pazifik, weil da kalte Strömung oben so im Ozean gibt und das kondensiert den Wolken da. Und von der anderen Seite den Anden blockiert die feuchte Luft. Und man hat hervorragende Konditionen da. Dunkel, ohne Wolken und die heutige weltgrößte Teleskopen sind da gebaut. The Very Large Telescope und da kommt gleich die Extremely Large Telescope und ALMA. Die Very Large Telescope sieht so aus, es besteht aus 4 Teleskopen jeweils mit 8,2 Meter Durchmesser gegenüber Galileos 25 Millimeter. Die Funktionsweise ist gleich. Alles Licht, das auf diese Fläche kommt, wird fokussiert auf eine kleine Pupille und in Kameras und man hat viel mehr Empfindlichkeit. Das ist eine Anlage mit 1 Milliarde Euro wert. Das ist Big Science und Big Ergebnisse. Da kommt gleich die Extremely Large Telescope. Das ist eine mit 30 Meter Durchmesser. Das wird auch in der Atacama jetzt gebaut. Und so sieht es heute aus. Weiter nördlich in Chile gibt es ein Radioteleskop, heißt ALMA. Das liegt auf einem Hochplateau bei 5000 Höhenmeter, ein sehr besonderer Ort. Aus vielen Einzelteleskopen, funktioniert aber gleich wie das optische Teleskop. Es sammelt das Licht und konzentriert es, oder die Radiowellen in diesem Fall, konzentriert es in eine Pupille und davon wird Bilder erzeugt. Aber warum brauchen wir so viele verschiedene Teleskopen? Das ist von diesen 2 Bildern erklärt. Auf der linken Seite ist ein Bild auf sein Flugzeug im optischen. Das ist wie das Auge das Bild sehen würde. Auf der rechten Seite gleiche Feld, aber in Infrarot. Und die sehen anders aus. Das Licht nimmt einen verschiedenen Weg. Es hat eine verschiedene Wechselwirkung mit den Blättern, mit dem Rasen, mit dem Wasser. Und man gewinnt verschiedene Informationen in die 2 Frequenzbereiche. Dann so auch machen wir in die Astronomie. Deswegen weil man mehr Informationen sammelt aus die verschiedenen Wellenlängen, brauchen wir verschiedene Teleskopen. So, das ist ein Bild von der Milchstraße. Wenn man in Chile oben schaut, wunderbar dunkler Himmel. Man hat diese Lichtstreifen über das Himmel. Und das ist unsere Galaxie. Es ist eine Scheibe. Wir wohnen in dieser Scheibe. Und wir sehen das von seitlich, also sieht es aus für uns wie eine Streife. Und das Zentrum ist in der Mitte und man sieht diese schwarze Wolken. Das ist Staub, es ist wie Rauch zwischen uns und was dahinter liegt. Und es blockiert unsere Sicht. Wenn wir in dem Infrarot blicken, das gleiche Bild, es sieht anders aus. Wir sehen durch den Staub, Infrarotlicht kommt durch den Staub und man gewinnt andere Kenntnisse. Und im Radiobereich von einem Radioteleskop sieht das gleiche aus wie das, nochmal anders aus. In diesem Fall ist die Strahlung von Gas, nicht von Sternen. Und hier color-kodiert ist die Bewegungen, wie schnell das Gas zu uns oder weg von uns fliegt. Unsere nächstliegenden Galaxien sind hier ganz andere Bewegungen. Man sieht eine Streife von Gas, das von dieser dahinter fliegt. Das ist, weil die durch unsere Milchstraße geflogen sind und hat Gas mit sich gezogen. Also verschiedene Teleskopen, verschiedene Sichten. Wir brauchen die alle, um ein komplettes Bild zu bekommen. In der Astronomie hat man interessante Aufgaben. Man hat oft nur einen Punkt von Licht am Himmel und man muss verstehen, was es ist. Die großen Fragen, die wir beantworten, ist oft die wichtigste Information ist, wie groß ist es, wie weit entfernt ist es, wie viel davon sind da und wie alt ist es. Und um das alles zu erkennen, braucht man aus diesem Punkt von Licht, was man nicht berühren kann, man kann nicht das im Labor machen, man kann keine Versuche machen. Man braucht alle Informationen aus so vielen verschiedenen Teleskopen, so viele verschiedene Blickwinkel, wie das geht. Und wir werden eine verschiedene Methodik brauchen, um die Folien zu wechseln. Geht das? Ja, gut. Also ich werde ein bisschen über die Astronomie reden, was wir mit diesen Teleskopen machen, was sind die aktuellen Themen. Eine große Frage ist, ob andere Leben im Universum gibt. Wir wissen diese Antwort noch nicht, aber wir sehen Orten, wo Planeten sich bilden. Und das ist eine von denen, das ist ein Stern in Ophiuchus in der Mitte und ein Staubwolken, das glüht um es herum. Und es gibt Gaps dazwischen, wo Planeten gebildet hat und diese ganze Gas ist in dem Planet ich werde ein paar überspringen auf zeitliche Gründen. Es gibt jetzt vielleicht 4000 Planeten, das wir jetzt kennen. Und in ein paar Fällen können wir die auch direkt sehen. Und in Beta Pictoris ist eine von denen. In diesem Fall ist der Stern in der Mitte blockiert, weil es zu hell ist, um das sehr schwache Licht von dem Planet zu sehen. Und über die Zeit, im Laufe der Zeit, man sieht die Bewegung von dem Planet. Das nächste Thema ist über schwarze Löcher und Neutronensternen. Die haben große Interesse für uns. Dieses ist die Entstehung von einem Neutronenstern. Das ist die Explosion von einem Stern in 1987 in Südhalbkugel. Ich habe das selber von meinem Haus sehen können. Ein ziemlich heller Stern, was einen Tag vorher nicht da war. Und in der Mitte von dem, ich habe 5 Minuten bleibt, ich werde vieles überspringen, um auf die Hauptthemen zu kommen. Okay, so ich überspringe zu Hubble, ein großer Name in der Astronomie. Er hat 2 besonders wichtige Entdeckungen gemacht. Und eine ist, dass unser Universum sehr groß ist. In seiner Zeit, das war das frühe 20. Jahrhundert, war das Universum unsere Galaxie. Er hat Sterne in die Andromeda-Galaxie erkannt, die gleich wie die gleichen Sterne in unserer Galaxie waren. Aber die waren sehr viel schwächer in Andromeda. Und das kam nur, weil Andromeda viel weiter entfernt ist. Es ist nicht ein Teil von unserer Galaxie. Der zweite, er hat entdeckt mit der weiteren Studie von diesen Galaxien, dass die alle von uns, meistens von uns, sich entfernen. Und er hat die Expansion vom Universum entdeckt. Er hat das damalige größte Teleskop in der Welt dafür benutzt. Wir haben diese Galaxien jetzt näher untersucht und viele von denen beobachtet. Und hier haben wir eine Sicht von oben, wo die sich befinden, mit Entfernung von uns und Position. Und man sieht, dass die Galaxien nicht zufällig gestreut sind. Es gibt eine Struktur hier, wie Spiderweb. Woher kommt diese Struktur? Das wissen wir nicht genau. Es kommt aus der Entstehung vom Universum. Das ist wie ein Fingerabdruck von der Entstehung und die Prozesse zwischen den Entstehungen und uns jetzt. Und die genauen Details, viel ist verständlich, aber genaue Details nicht. Es gibt Physik, was wir noch nicht verstehen, und das würden wir sehr gern untersuchen. Das ist eine von unseren größten Fragen. So, mit Teleskopen, die sind Zeitmaschinen. Wir sind jetzt hier und wir schauen zurück an die Urknall, am Anfang. Je weiter man schaut, desto weiter zurück in die Vergangenheit sieht man, weil Licht braucht Zeit, um das Teleskop zu erreichen. Und insgesamt 13,8 Milliarden Jahre alt. Wenn wir ein Teleskop hätten, die so weit sehen könnten, würden wir die ganze Geschichte und den Ablauf vom Universum, Entstehung und Entwicklung sehen können. Ich überlagere hier diese Beobachtungen, was wir bis jetzt gemacht haben. Und wir erreichen nur diese Entfernung. Und wir wollen hier sein. So, auf einer Entfernungsskala, wir sind hier, wir können bis da gut messen und wir wollen Faktor 10 weiter blicken. Unsere Teleskopen, ich komme aus Australien, also nutze ich Effelsberg. Mit Parkes. Mit Parkes kann man hervorragend die naheliegenden Galaxien sehen, mit 2000 Quadratmeter Fläche. Auf 1, die zu kommen, nutzt man die größten Teleskopen jetzt, mit Sammelfläche von 10.000 Quadratmeter. Unglücklicherweise, um einen Faktor 10 weiterzukommen, braucht man ein Teleskop 100 Mal größer. So, das bedeutet eine Sammelfläche von 1 Million Quadratmeter, die Square Kilometer Array. Es gibt die Vorläufe in der Richtung zu bauen. In Südafrika im Moment die Meerkat Array mit einer Sammelfläche von etwa 10.000 Quadratmeter. Das ist nicht größer als, das ist noch nicht das größte in der Welt, aber es produziert schon beeindruckende Bilder. Es gibt viel Detail da, was wir nicht vorher gesehen haben. Viel von diesen Linien, die wir nicht verstehen, ganz. Ziel ist, 3000 solche Antennen über dem zu erweitern mit einer Sammelfläche von 400.000 Quadratmeter. Das ist nicht ganz 1 Million. Aber große Fragezeichen ist über den Kosten. Wenn ich das hochskaliere vom Meerkat, kommen wir auf 15 Milliarden Dollar. Und das wäre unbezahlbar teuer. Aber wenn wir an die schon existierenden Solarkraftwerke schauen, diese Sammelfläche, über 1 Million Quadratmeter, das existiert schon. Wenn wir das für die Astronomie nutzen könnten, würden wir sehr kostengünstig ein großes Teleskop haben, was uns am Ende das Universum bringen würde. Und so unsere Idee ist, einen Empfänger oben zu platzieren und die ganze Sammelfläche beim Nacht zu nutzen. Und das ist nicht der einzige, es gibt viele davon in der Welt. Die Orangen hier sind schon im Betrieb, die Blauen sind vorgeschlagen, manche sind im Bau. Der in Chile sieht so aus, verglichen mit dem jetzigen größten Teleskop in der Welt. Diese Fläche ist jetzt komplett mit Spiegel verdeckt. Und das größte Teleskop im Moment ist in China mit 500 Meter Durchmesser. Das ist der anfänglich in Spanien. Von Boden aus sieht es so aus. Die Strahlung ist gebündelt auf einen Wärmetauscher. Unsere Idee ist, einen Empfänger ganz oben beim Nacht zu nutzen und man justiert auf dem Spiegel. Vergleich mit Effelsberg. Raytracing. Wir haben ein technisches Problem, wenn das Ganze in den Brennpunkt kommt, in der Pupille, um das durch die Pupille zu kriegen. Die bundeln nicht genau, wie man das haben wollte. Die Strahlung im Brennpunkt ist sehr verstreut. Man würde gern so einen Punkt haben, damit die Pupille ganz in der Mitte liegt. Aber dieses technische Problem überwinden wir mit einem Radioempfänger, das etwa so aussieht. Statt ein normales Auge, das nur ein Element hat, würden wir mehrere tausend Elementen haben, die diese ganze Energie sammelt. Und das ist wie das Auge von einem Insekt. Wir machen einen kleinen Versuch zuerst. Wir haben in Jülich eine Versuchsanlage, das hat schon eine gewaltige Sammelfläche, das ist schon größer als Meerkat. Wir bauen schon Empfänger dafür, um die erste Versuch zu machen. Und ich freue mich, das ist meine letzte Folie, ich freue mich auf die Zeit, wann wir einen Empfänger auf dem Turm in Chile haben, auf Cerro Dominador. Und diese kleine Linse von Galileo, die 25 mm Linse, würde dann vergrößert sein auf eine 3 Kilometer Linse, damit wir bis zu Ende des Universums sehen könnten. Danke sehr.
So, vielen Dank an Ellen. So, jetzt seid ihr gefragt. Gibt es Fragen? So, die Frage, die... So, die erste Frage, die gestellt wurde, ist, normalerweise kann man so ein Teleskop, so ein Radioteleskop ja ausrichten, aber das hier ist ja fest und der Empfänger ist auch fest installiert. Kann man, also was ist dann, wie kann man damit quasi eine bestimmte Region am Himmel beobachten?
Die sind glücklicherweise nicht fest. Der Empfänger selber ist fest, aber der Spiegel ist beweglich. Es ist schon ausgelegt, um die Sonne zu folgen. Und vom Sonnenaufgang bis Sonnenuntergang. Und wir brauchen eine kleine Softwareänderung, damit er andere Quellen folgt, unsere Quellen.
Okay, ich glaube, da gab es noch mehr Fragen, oder? Ja.
Wird der Empfänger tagsüber aus dem Turm rausgenommen? Ist er temperaturempfindlich?
Der Empfänger ist natürlich temperaturempfindlich. Es würde aber in einen verschiedenen Ort liegen als die Wärmetauscher. Also tagsüber würde die Spiegel an die Wärmetauscher gerichtet sein und beim Nacht höher oben.
Okay, noch mehr Fragen. Also wenn ihr Fragen habt, einfach irgendwie in die Nähe der Bühne kommen, damit ihr eure Fragen stellen könnt.
So, hier.
So, hallo Alan. Ja.
Hi Ivan.
Ich gratuliere dich für den sehr interessanten Vortrag. Also du hast eben gesagt, es gibt so viele solche Solaranlagen auf der ganzen Welt. Kannst du dir so Interferometrie zwischen den verschiedenen Solaranlagen weltweit vorstellen? Und wie weit würde man kommen?
Ja, es gibt mehrere solcher Anlagen. Es ist sehr spannend, wenn man mehrere davon mit Empfänger ausstattet, um die zu vernetzen. Und dann würde man ein Teleskop so groß wie die Erde haben. Das gibt uns sehr scharfe Bilder, aber auch mit sehr hoher Empfindlichkeit. Und die Empfindlichkeit ist so hoch, dass man eine komplett andere Art von Objekt sehen könnte, als wir bis jetzt mit dieser Technik beobachten. Nämlich, man würde thermische Quellen sehen, nicht nur nicht-thermische Quellen. So würde man Sternen mit dieser Technik sehen können und Sternen sehr gut auflösen.
Das klingt ja wirklich sehr spannend. So, gibt es noch mehr Leute, die Fragen haben? Da hinten. Kannst du irgendwie kurz hier hinkommen? Das wäre, glaube ich... Okay, die Frage ist, warum kann man mit einer größeren Fläche quasi weiter zurückschauen, also eine höhere Auflösung bekommen?
Das Problem ist, wenn Galaxien sehr weit entfernt sind die entsprechend schwach und die verschwinden im Rauschen und man sieht die nicht. Wenn man eine große Sammelfläche hat, hat man genügend Photonen von dem weitliegenden Objekt, damit man die sehen können.
Okay. Noch mehr Fragen? Da vorne?
Sind die Interferenzen oder das Rauschen durch Schmutz auf den Spiegeln nicht zu groß? Und ich meine, die Spiegel sind ja auch nicht dafür gemacht, sehr genau eingestellt zu werden. Kriegt man die überhaupt auf einen Punkt ausgerichtet, so genau, dass man da erkennbare Bilder daraus produziert?
Zum Glück für uns kommt Radiowellen durch Staub und Schmutz sehr, sehr gut. Das verhindert kaum. Die Justierung von dem Spiegel spielt ein bisschen von einer Rolle und wir fangen an mit einem Projekt, um das zu bestimmen in der Anlage, wie gut ist die Steuerung. Aber zum Glück ist es nicht sehr kritisch, weil die Wellenlänge ist sehr lang und die Spiegel sind ziemlich klein. Also es ist die Zahl für Jülich, wir wissen, die sind schon 100-mal besser, als wir benötigen. So, wir haben wenig Angst auf diesem Punkt, aber wir müssen das bestimmen.
Okay, dann würde ich sagen, noch einmal vielen Dank an Ellen und großen Applaus.
So we will go on a small break very soon, but before that, we always have announcements. So as I said, we have a lot of prizes today, a lot of exciting Astro swag for you. And obviously, they are sponsored by someone. We're obviously very, very happy with the sponsors. We thank them all the time. If you like the prizes, then, remember them, join them on Instagram, things like that. But our sponsors today are from European Southern Observatory, ESO. So we have Astro swag from them. Then we have Euclid, I believe, yes, Euclid Astro swag, and Astron, which is the radio astronomy in Netherlands department, observatory, sorry. Yes.
Ja, und wir haben natürlich auch wieder mal unsere Sponsoren dabei und von denen liegen auch einige Sachen auf den Tischen. Also da könnt ihr euch einfach bedienen und zugreifen. Unsere Sponsoren sind einmal die European Southern Observatory, ESO, dann auch die Euclid-Mission und Astron, das niederländische Institut für Radioastronomie.
So in order to get all these prizes, you can participate on the quiz and you will get a raffle ticket and you have a chance to win. Or you can give us a small donation, and we are very happy with your small donations. Thank you very much in advance. The idea of the donations is that we actually can carry on with the event, so printing posters, doing advertisement, different things. And the way that we ask for your donations is by voting over a question. And today we want to ask you, what telescope do you like more, Hubble or Jwst? So Hubble was a telescope from 1990, and it observed in infrared, optical, and UV, I believe, yes. And Jwst will go soon on space, very soon. Since last year, it's very soon going there. But hopefully next year it will launch, and it will observe mostly in infrared. Yes. So if you like one over the other, you can give your donations. Eleni and Manali will go around with the two glasses. You can vote with any kleine Spenden, any small amount of money you want to give, and we'll give you a raffle ticket and you can win a prize.
Genau. Und damit kommen wir auch wieder zu unserer Bierglasabstimmung. Und zwar funktioniert das folgendermaßen. Unsere Glücksfeen Eleni und Manali werden gleich rumgehen mit 2 Biergläsern. Und da könnt ihr euch entscheiden, ob ihr lieber das Hubble Space Teleskop oder das JWST Weltraumteleskop mögt. Das Hubble-Teleskop, davon habt ihr sicher schon mal gehört. Das hat zum Beispiel das Hubble Deep Field gemacht. Das ist schon seit 1990 in Betrieb, das Teleskop. Und das beobachtet hauptsächlich im infraroten, optischen und im ultravioletten. Es gibt auch bald eine neue Mission, nämlich das JWST. Und das beobachtet hauptsächlich im infraroten. Und das wird, es ist gesagt, dass es ungefähr 2021 starten soll. Und wenn ihr jetzt für eins der Teleskope entscheidet, packt ihr einfach, wenn ihr wollt, eine kleine Spende in eins der Gläser und dann könnt ihr auch gleichzeitig an unserer Verlosung teilnehmen. Und dabei könnt ihr wirklich tolle Preise gewinnen. Da haben wir uns heute nicht lumpen lassen für unseren Geburtstag. Das heißt, ihr könnt zum Beispiel einen Kinogutschein gewinnen oder auch ein Buch oder auch eine unserer tollen Astronomy on Tap Flaschen. Also spendet fleißig für unsere Sache, bitte.
So some of the prizes that you can win are some voucher for the Kinopolis, some AOT bottles, something from ESO, some mug glasses as well. And yeah, please donate. We're very happy. The last thing, and then we go for break, I promise, is we're going to have a break for 10 minutes. Kevin, our dear member of AOT, will play drums again. And today we have new drums for you, so exciting things. 3 drums this time. And yeah, so we'll see you in 10 minutes.
Jetzt gibt es noch gleich eine kurze Pause und danach findet unser Astro-Quiz statt, das von Sandra moderiert wird. Also auf jeden Fall nicht zu weit weglaufen, damit ihr das noch mitbekommt. Und in der Pause wird unser Kevin jetzt uns eine kleine Trommelvorstellung geben. Also bis gleich.
The light is blinding me so much. Hallo an alle, die gekommen sind, die ich nicht sehen kann, weil das Licht so blendet. Aha. We want to start the quiz. Wir möchten das Quiz starten. Das Quiz ist wie immer zweisprachig. The quiz is, as always, bilingual, that everyone here in the room can participate. Ich möchte, dass ihr alle mitmachen könnt, deswegen ist es zweisprachig. Ihr dürft zweisprachig antworten, ihr dürft zweisprachig rumraten und die Regeln erkläre ich dann immer so, wie sie gerade kommen. So you can answer in both languages, I don't care. The only problem maybe that I really don't see anybody here. And yeah, I hope that you donated some cents to us, because if you did, you have the chance to win great prizes. And the best thing about that, even if you not did, you still have the chance to win great prizes. Ja, also ich hoffe, dass ihr was gespendet habt, weil ob ihr nun das gemacht habt oder nicht, ihr kriegt Preise, aber ich würde mich zumindest freuen. Wer hier schon mal war, der kennt dieses Spiel, und zwar müssen wir dafür den Raum in zwei Seiten teilen. If anyone of you has been here before, then they know that we have to divide the room in two sides. So now you can look to the left, you can look to the right, and then gauge whether you sit on the correct side or not. Ja, also ihr könnt jetzt nach rechts und links gucken, ob ihr euch auf die richtige Seite gesetzt habt, weil wir werden den Raum teilen, und ich nehme mal diesen schönen Holzbalken hier. Derjenige, so we use this dividing piece of wood here in the middle, and you, mister, with the Adidas sweatshirt, you have to decide now on which side you want to be. On this side. Okay. Let's see whether this was a wise choice. Okay, also, wir haben hier ein Team, alle bei diesem Tisch auch sehr schön, ja, also nicht zusammen, nicht schummeln. So. Alle vom Tisch auf dieser Seite sind ein Team und alle hier auf dieser Seite. Ihr seid ein Team und ihr gewinnt zusammen. You win together, okay? This game works. You have on each side two helping AOT members, Astronomy on Tap members. On this side, we have Anne and Florian helping you. Yeah. And on this side, you got Eleni and Manali. So one red person on each side. And ja, also auf der rechten Seite Anna und Florian für irgendwelche Fragen, die kommen. Und auf der linken Seite Anna und Manali, weil ich kann hier vorne nicht sehen, wer zuerst seine Hand hochhebt. I can't see here in front who's raising the hand first. So you guys have to help me and then shout as soon as you see someone raising the hand. Ich starte immer mit einer kleinen Testfrage, die ist super einfach. I always start with a short test question, just to see whether everyone got the rules. Just raise your hands, don't shout. Ja, also wenn ihr die Regeln verstanden habt, einfach Hand hoch, nicht reinschreien. Hier die einfache Testfrage. Und which month will Astronomy on Tap be 1 year old? Welchen Monat wird Astronomy on Tap ein Jahr? Okay? Too late. Ja? September. Ja. As I said, a test question. Das war eine Testfrage. And this is how the game goes. We have different categories. Wir haben verschiedene Kategorien von dem Spiel. And I will explain them as they come. Ich erkläre die, wie die so kommen. So, yeah, please shout at me. Do something that I reckon. No, you did not. Okay, let's start. Are you ready? Any questions to me left? Gibt's noch Fragen an mich? Das ist gut. That's good. First category, erste Kategorie, Astro News. As you all, every day look into the news of what's happening in astronomy, like me. I have just two short questions, what happened in the last month. In der ersten Kategorie möchte ich allen, die ihr die Nachrichten jeden Tag verfolgt, ob nur im Radio oder im Fernsehen, einfach fragen, ob ihr mitbekommen habt, was in den letzten Monaten Großartiges in der Astronomie passiert ist. Und das wird jetzt der erste Punkt werden. This will be the first point, whoever answers first. Okay? So, start. Welches Kleinstlebewesen war an Bord der israelischen Bereshit und zerschellte letzten Monat auf den Mond? Which microanimal was on board the Israeli Bereshit and crashed on the moon last month? Ja? Again, please? Water bears or tardigrade or Bärtierchen. This really cute microanimal can literally survive everywhere. Probably he'll even be able to finish a degree in physics. So he can survive hot temperatures, cold temperatures, strong pressure, low pressure, every kind of inhuman thing you can imagine. And also it was on board of this Bereshit mission, and it crashed, and this was in some kind of sleeping state, but scientists believe that some might survive, so that makes it the first living animal on another thing in space. Jetzt nochmal auf Deutsch. Also die Bärtierchen sind unfassbar widerstandsfähig. Heiße Temperaturen, kalte Temperaturen, großer Druck, kleiner Druck, die können alles überstehen, sogar ein Physikstudium. Und die waren an Bord der Bereshit, der letzten israelischen Raummission, die leider zerschellt ist am Mond. Aber jetzt gibt es gute Chancen, dass ein paar von denen die Explosion überlebt haben und weiterhin auf dem Leben sind. So, 1-0, nothing decided yet, 1-0. And we keep going. Second question, be ready. Are you ready? And go. What was found for the first time in a habitable super-Earth atmosphere? Was wurde zum ersten Mal in einer habitablen Super-Erde-Atmosphäre gefunden? Let me finish, please. I heard you. Okay, I just wanted to finish the question. So? Wasserdampf, water. That's correct. Also das ist eine künstlerische Darstellung von diesen Planeten mit der Telefonnummer K21. I wrote it on my K218b. Das ist zweimal so groß wie die Erde, 8-mal so schwer, relativ ungemütlich. Ihr würdet alle 8-mal so viel wiegen, aber eine ganze Menge an Wasser wurde da gefunden. Vielleicht einer der ersten Planeten, wo wir extraterrestrisches Leben finden werden, in welcher Form auch immer. So this is the planet K218b, my goodness. Yeah, 18b, telephone number, you can call it. And they found actually water on this planet. By making fancy observations as we always do. And that might be the first planet, one of many where we find water, which is one of the key ingredients to find life. Maybe even intelligent life, some things that we are lacking on Earth nowadays. Okay, let me just continue before I make some foes. So the next thing is, it's about logic, okay? You will see a picture now, and there will be a question mark in the middle, and I want you to find out what should the question mark look like. I am aware that you don't have any pen and paper, so please use your two arms. That will be enough to indicate to me what the solution will be. Whatever I just explained will be clear as soon as you see the picture. Yeah, raise your arms maybe like this or like this to indicate the solution. Die nächste Kategorie hat was mit Logik zu tun. Ihr werdet jetzt gleich ein kleines Rätsel sehen und ihr müsst eure zwei Arme benutzen oder einen Fuß oder was euch so einfällt. Und dann zeigt ihr einfach mal die Lösung dazu, okay? Ist ein Logikrätsel. Da kann man gar nicht viel zu erklären. Und, are you ready? By the way, it's 1-1. It has nothing happened yet. And go. Find the question mark. Can you see it, all of you? So there's some logic behind that, and I assure you that's the easy one. Oh. Okay, wait, I need to see you. Yes! So this was correct. He said he did this, which is sufficient for me. So what you just had to do, was ihr eigentlich nur hätte tun müssen, ist die erste Reihe und die dritte Reihe einfach quasi aufaddieren und dann kommt die Mitte raus. So you just had to add visually the first row and the third and find out what's in the middle. And yeah, the team to the right, at least for me, solve it, so it's 2-1 now. But don't worry. Yeah, I know why you say boo. I requested a bikini girl too. But never mind. Yeah, bikini man, I don't judge. It's fine. But Felix, you know, showing up in... Nah. Anyways. Es gibt noch ein zweites Logikrätsel. There's the second one. So please be ready. And now I want you, so you don't have to do any exercises now. Maybe that was your problem, that you didn't want to raise your hands. You just have to tell me the numbers now that are supposed to be in the last line. And go. I really don't want to break your concentration, but I had 5 mathematicians spending an hour on that. Yeah. Okay, please. 13? 9. Yeah. That is correct. So, the answer is, in the first line, in der ersten Linie, ihr habt eine 1, there's 1, 1. In der zweiten Linie sind 2 Einsen, 2 ones. And in the third line, there's, 1, 2, and 1, 1, and then there's 1, 1, 1, 2, 1, and 2 ones. So now we have 3 ones, 2 twos, 1, 1. And next is 1, 3, 1, 1, 2 twos, 2 ones. Okay, ja. Das war sehr gut. Das heißt, die Punkte sind 3-1. Sehr gut, sehr gut, sehr gut. Yeah, and since one of the teams doesn't seem to like the logic questions, we switch the topic now. Eins der Teams scheint Logik nicht so gerne zu mögen, also wechseln wir jetzt mal das Thema. Und die neue Kategorie ist Schätz mal. Das funktioniert so. Also wir fangen mal mit dem Team an, was gerade nicht in Führung liegt. Das wäre jetzt nur im Moment das Team auf der linken Seite. Ihr sagt mir gleich eine Zahl. Ihr habt 1 Minute, um euch eine auszusuchen, bitte mit Einheit. Sonst wird es immer schwierig. Und das zweite Team sagt nur mehr oder weniger. And now I repeat in English. This game is called Take a Guess. So we always start with the team that's struggling at the moment. And you will see a question. You will come up with a number. Please give me a unit. Otherwise, it's always a bit complicated. I just put apples then, if you don't give me a unit. And whatever you say, this team just has to decide in more or less. Your very beautiful and charismatic helpers on each side will help you to collect a number. And we start with the first one. Or do we have questions? Gibt's noch Fragen? Nein. Gut. The first one is the furthest distance any human being has ever been from any other human being. Oder auf Deutsch, die größte Distanz, die ein Mensch jemals von irgendeinem anderen Menschen war. And I want to give the hint that if you travel on a ship, you're probably not alone. Ja, also wenn ihr auf einem Schiff seid, auf der Reise um die Welt seid ihr meistens nicht alleine. Nur so als Tipp. And you have 1 minute. You give me a number, you say more or less. Go. Aber ich glaube, es ist noch niemand aufgefallen. 20 seconds, noch 20 Sekunden. Ten seconds, 10 Sekunden. Eleni, 10 seconds, 5 seconds. 4, 3, 2, 1. I need an answer. 400 kilometers is the answer from the team on the left side. 400 kilometers, is that correct? 400 Kilometer. Yeah. And now I need to hear from the team on the right. Okay. Hoch die Hände, raise your hands for more. And now, hoch die Hände, raise your hands for less. Okay. Let's find out what was the furthest distance any human being was like totally alone anywhere, and it is 4.585 Kilometers. Es waren 3.585 Kilometer. Und zwar, please listen before you complain. Zuhören. So this is a very, very accurate scientific chart. So there was this 2 astronauts on one side of the moon, and then there was a third on the other side of the moon. So you just need the diameter of the moon, right? Ja, also bei der Mondlandung gab es diesen einen Astronauten, der zurückgeblieben ist, und der war halt dann zwischenzeitlich mal auf der anderen Seite des Mondes. Und da war der definitiv alleine. Haha. Gut. So now it's 4-1. We do the same thing again. Yeah, clap for yourself. We do the same thing again, but we reverse sides. So now you tell me a number, you say more or less. Und jetzt dasselbe nochmal, nur umgedreht. Ihr sagt mir eine Zahl, ihr sagt mehr oder weniger. Und die Frage ist, ausgehend von der lokalen Dichte der dunklen Materie, wie viel davon findet man auf der Erde, bitte mit Einheit? Assuming the local average density of dark matter, how much do you expect to find on Earth? Please give me a unit. This time, I think apples is kind of fine. One minute, eine Minute. Ich sehe gar nichts. Yeah, but they need a minute. So no more quiz?
Do another one.
Yeah, it's like 4 more questions. So? 4 more questions. Okay, I try to hurry. Yeah, I go fast. 20 seconds more. 15, 10, 5. Anna, how is it going, Florian? 10, 9, 8, 7, 6, 5, 4, 3, 2, 1. I need an answer. Give eine Antwort. Anna, ich möchte eine Antwort. 1 Gramm, 1 Gramm. So now, as before, 1 Gramm, 1 Gramm, you gotta raise your hands for more. You gotta raise your hands for less. And who did not understand the question? Okay. 1 Gramm für 1 Gramm mehr? Nein, nein, einfach nein. Okay, nein, ist mir egal. mega. We go to the solution, so the right side, at least for me, said 1 gram, 1 Gramm von rechts, weniger von links. It's, nothing happened. 547 grams. It's almost the weight of a typical squirrel. Also so ein typisches Eichhörnchen. Ihr könnt jetzt in den Wald gehen und das eine dunkle Materie-Eichhörnchen finden. You can go into the woods and find that one dark matter squirrel. What is it? Ja, die haben. Nee. Die. Ja, aber es ist ja mehr. Also haben die recht.
Ja, die haben recht.
Ja. Achso, okay. So guys, listen. Eleni, that's her, said I have to hurry. So we have to hurry now. I hurry you, okay? Next category is depixelation and pixel. So you see a very coarse image, it gets better and better and better, and you have to find out what it is, 1 guess per side. And then we go to the next image. Ja, also ziemlich schlechtes Bild und ich mache immer, die Auflösung immer besser und sobald ihr es wisst, Hand hoch, eine Chance pro Seite. And go. How hard can it be? Next. Yeah, she's seen the quiz, that's what she knows. We don't have time, so I move on. Was? No, it's not Ultima Thule. It's Effelsberg, that is correct. Okay. Thank you very much. Vielen Dank. That was correct. And I like that you get excited, but we gotta move on. Next image. Next image. Komm, jetzt, it's easy, no? Next. Yeah, you can guess, no? It's Pluto! Nicht zu verwechseln mit Pluto von Mickey Mouse. Yeah? Not to, okay. Okay. So, someone said I have to stop. What is your opinion about that? They can win. They can get 8 points in the next round. So do you want to continue? Okay, we stop. I ask again, do you want to continue? Okay. Ihr habt mich überzeugt. The next one, you can get more points. It's a totally new design, thanks to Sven Heidenreich at this point, who couldn't be here. Thank you, Sven, if you're watching, I don't know. Anyways, you'll meet him next time, new member. It's Ordnung muss sein, sorted out. I go quickly over that. So you get now 5, you will see 5 things on the next slide. Your very beautiful and charismatic helpers have them as cards, and you will sort them for me. And then we check whether they're correct. Correct means 2 following cards are correct. So you start with 1, then you get a point, and if the next card is correct, you get another point. The next card is correct, you get another point. The next card is incorrect, you don't get a point. See, that's how it goes. Doesn't really matter. So you can get at most 10 points here and at least 0 points. The first one is these 5 objects. I don't give you any details about them. I'm sorry that I don't translate, but we're in a hurry. It's these 5 things, and you have to sort them by size. You have 1 minute. Sort them. You have to sort them. You done? Then give them to me in a staple. Start with the smallest. Okay, thank you. Anna. What's with the rest? Hurry! Seconds left. What didn't reach me. 15 seconds left. 10, 9, 8, 7, 6. Anna, that goes into your direction. 5, 4, 3, 2. What's your secret? And that's it. Last chance. 3, 2, 1. Now that was close. Okay. Both teams started with the asteroid, Ultima Thule. Go on. Click. I clicked. I swear. Click. Nothing happens. Ah yeah. Woo! You get a point each side. The asteroid was correct. 35 kilometers max. I know it's not a circular object. That's the maximum diameter it can have. Next one. So, I think the left side said Pluto and the right side said M87 event horizon. Did you say event horizon? That's your fault. I started with a fucking asteroid and then you give me this and I have it the wrong way around? I'm sorry. So next one is Pluto, that is correct. 2,400 kilometers. So you both get a point. I think that is too easy. And then the next one, it's the sun with 1.4 million kilometers. Man, you have everything correct. That's really disappointing. Then this very, very large star that I don't even try to pronounce. And you both got it correct. And this is the last one. M87 supermassive black hole event horizon. And now we do the whole thing again, if the presentation is working. And now you sort, please, by number. And we cut it. You want to know the solution?
No, we're going to say that in the next slide.
Aha. I'm sorry. Okay. I hope it was still a fun game. Ich hoffe, es hat allen Spaß gemacht. Mir macht es immer Spaß. Heute, aber nur heute, today, just today, won the side on the right to me. Congrats. of you now get a special raffle ticket with a special color, which is blue. With a special blue color, and then you get 5 prizes just on your own. Like totally, if you contributed to the donations or not, doesn't matter. You won. You get 5 prizes. It can be a bottle, it can be a book or a cup or whatever you see in the picture. And I hope to see you next month again.
So after a very exciting game where the right team won, now we have our second talk of the day by Dr. Andrei Lobanov. And he did his master's in 1991 in astronomy at Moscow University. Are you Russian? I didn't know that. So we have a Russian today. In 1996, he got his PhD at the Institute of Physics in New Mexico Institute of Mining and Technology in Socorro. And at the same time, he was actually working at the National Radio Astronomy Observatory of the US. Yes. And since then, once he graduated, he actually moved to Bonn and he's been working at the Max Planck Institute for Radio Astronomy as a postdoc and then as staff scientist. And he works on ground and space observations. And he works with the VLBI. Yes, yeah, correct. And since 2010, he's actually a visiting researcher at the Institute of Experimental Physics at the University of Hamburg. And he's working on direct dark matter searches, which is very, very cool. And today he will tell us about many phases of interferometry.
Also unser zweiter Vortrag ist heute auf Englisch, und zwar von Dr. Andrei Lobanov. 1991 bekam er sein Master of Science in Astronomie von der Universität Moskau und 1996 sein PhD vom New Mexico Institute of Mining and Technology in Socorro, New Mexico in den USA. Währenddessen arbeitet er auch schon am National Radio Astronomy Observatory dort. Seitdem ist er Postdoc und später auch dann wissenschaftlicher Mitarbeiter am Max Planck Institute für Radioastronomie hier geworden und arbeitet speziell mit VLBI und noch speziell mit Weltraum-VLBI, wo er wahrscheinlich gleich noch darüber erzählen wird. Und seit 2010 ist er sogar Gastwissenschaftler in der Universität Hamburg und beschäftigt sich dort mit der Suche nach dunkler Materie. Also jetzt auch nochmal einen großen Applaus für Andrei Lobanov.
Thank you. So I want to use my 20 minutes of fame to give some thoughts about the endeavors of interferometry, which is the science which I have been doing ever since I started my master's thesis in Moscow. So interferometry is in fact is a very simple thing. It's when you ask yourself a question, if I have 2 or 3 raindrops falling into water, what happens with these circles, with the waves which collide with each other? If you can answer these questions, you can master interferometry. In fact, if you can answer that question properly, you can use that information that is in these collision points between different raindrops to infer something about the falling stones in the water. So it is seemingly such useless or nonsensical questions that start the scientific endeavor. And the problem with scientific endeavor is that it usually takes such a long time that you cannot even predict which way it will take you once you start asking these questions. But I think it's probably the most human type of activity that we can enjoy on this planet. If you ask yourself the question, what's beyond my horizon? Just like this man here, this in engravings of Camille Flammarion, the Voyager, that just looks outside of his heavenly sphere and sees new horizons, new places. So with interferometry, the endeavor in interferometry was also starting a very long time ago, about 350 years ago. And we're starting with some man named Isaac Newton, asking also usually quite nonsensical questions and uninteresting questions maybe. What happens with light if you put it through pieces of glass? And not only was asking this kind of questions, he was also doing damage to the royal properties in Cambridge, because anecdotal evidence says that he was, for his experiments, he was destroying the shutters of the windows or curtains of the windows of the royal palaces in Cambridge. So somebody allowed them to do that. And because of he was allowed to do this, he made a very important conclusions. He thought that light is actually, when it bends and breaks into a several colors in the once it passes the prism, that light consists of particles. And then started a big debate, because before, after the invention of the telescopes, everybody was thinking that light was waves. And here comes Newton and says it's particles. And it's actually made a very big influence on the entire scientific debate for about 100 years, because Newton was such an authority, probably as big as authority as Einstein for us, that nobody was actually having guts to object to that and saying that it's not just particles, probably wave. And so it took about 150 years, almost 150 years, before people were studying, amassing evidence that it is very difficult to understand many phenomena once you assume that photons or light is just particles. And this was the groundbreaking discovery, groundbreaking experiments made by Thomas Young. They're called double slit experiments. When you ask yourself the questions, what if you look into the room not just through one, but two keyholes at once? So in essence, you just light two small keyholes and ask yourself a question, what happens with light once it passes them through? And what he found out is that the light then forms a very peculiar patterns with light and dark stripes on the screen. And his conclusion was that the only way it is possible if light is actually waves. So that was one of the definitive arguments that light should have a wave-like nature. Well, since then, we know that light is actually waves and also particles and many other things, waves and particles, probably everything, waves and particles, which only means that we don't really know what it is. It's probably something beyond that, but we need to keep asking this kind of questions, and then we should be able to answer, or not answer, but give a better type of answers to some enigmas of the universe. So, luckily for Young, he was not alone. There were many other people investigating similar phenomena in optics, talking about what's going with the light when it passes through different types of lenses. And what they found out is that when the light passes through lenses, you get a response which is similar to what Young found in his experiments with the double slits. So these two patterns here, one of the stripes that comes from the Young's experiments with two slits, and another one stripes or circles which come out from diffraction response of a lens. And these patterns are all both proportional to the lambda, to the wavelengths of the light at which you use to produce them, and to the size of your experimental apparatus, which is the diameter of the lens, or the separation between the two slits. So from that, you can come to a conclusion that these things are actually similar and have a similar nature. And moreover, that you can actually, if you start producing these two slits in all kinds of configurations, so that you cover, say, 2 points on this lens, every 2 points will be just connected with each other through this kind of setup, you would be able to reconstruct the performance of a lens just from performances of many of these two slits arrangements. This was, or may have been, the thought, but it took another 150 years before you can actually turn these thoughts into real instruments. And it was happening in radio astronomy, because instead of these two slits or two holes in your lens, radio astronomers were using two telescopes put in different locations. And then you combine the signals from these two telescopes, and by combining the signals from more than two telescopes together and producing these pairwise combinations of those, you can actually reconstruct the telescope, which would be equal, the diameter of which will be equal to the largest separation between the telescopes you're actually having. So this is illustrated here, for instance. This is the locations of antenna of the American telescopes of Very Large Array. And you see this black line connecting the two antennas. So if you look at these two antennas as two holes of the Young's experiment, two slit experiments, this is the pattern. On the right-hand side, you see the pattern from that double slit that comes out from these two antennas. If you look at the other two antennas, different combinations, you see that pattern changes because it's proportional to the separations of the slits, and also depends on their orientation. So now, if you just combine all possible pairs of antennas in these 27 antenna telescope, and you combine these patterns, which come from every pair of these antennas, you will get a pattern which is already resembling a point spread function, or the PSA, or the lens response you see on the right-hand side. And on the left-hand side, you see all these possible combinations, basically plotted, all possible pairwise combinations of different antennas. So they form just nice pattern here of 6-point stars. And the actual pairs of antennas which I showed before, you see them marked here with the red circles. So now this is good, almost good enough to combine it or to produce a big lens. But we want a lens which is actually totally filled. You see the dots here, they do not fill the entire circle. So what you can use to help yourself with reproducing or producing such a virtual lens is the Earth rotation. Because if you let this telescope sit there and look at this object for about 1 hour, each of these points will move because the telescope's orientation with respect to the sky will change. So you will get situations like this. So within 1 hour, your pattern changes, and the resulting response of a lens, if you see on the right-hand side, slightly improves. If you sit for 3 hours, it gets even better. If you continue for about 12 hours, you see on the right-hand side, you almost a perfect response of a normal lens. So you reconstructed the telescope with an effective diameter of about 30 kilometers. So this is the essence of the interferometry. That's how the interferometric instruments work, not only in radio, but also in other domains. And now what I want to do for the rest of the talk is just basically give you the examples what we can do with our interferometric experiments and interferometric instruments, and mostly with the instrument called very long baseline interferometry, where you take these telescopes and they're separated not by 30 kilometers, not by 100 kilometers, but they're spread around the entire Earth. So the maximum separation will be about 12,000 kilometers. And you can add even the telescopes which would be in space. At the moment, we're working with a telescope which was as far away from the Earth as about 350,000 kilometers away from the Earth's surface. So what it gives us is that you know that in sensitivity of your instrument is proportional to the telescope diameter, or squared of the telescope area, and resolution is the wavelengths divided by telescope diameter. So with interferometry, if you add more telescopes, several telescopes together, then your sensitivity is determined by the sum of their areas. And the resolution is then given, as I said, by the largest separation between those telescopes. So you can really achieve very, very interesting results by doing this kind of applications. So the sensitivity of the radio astronomical telescopes have changed by a factor of more than 1 million ever since the first radio telescopes came about, since 1940, the first telescopes here. And then you see how the sensitivity improves with time. And all of the telescopes marked with the blue circles there are not a single dish instrument or a single telescope. Those are all interferometers, so combining many antennas together to work with that. So with the planned or future next generation radio interferometers such as SKA, we will be able to achieve such a good sensitivity to the radio signals that you will be able to see or to overhear the eavesdrops on the airport radar in a planet of about 50 light years away. So you could, if there is an airport there, you could actually see what they're doing there. You would be able to see something as minute as about an event that lasted of 1 nanoseconds. This is the computer capabilities of these new generations of telescopes. And you can measure the velocities of moving bodies to accuracy of about 1 centimeter per second. And there's another interesting aspect of the sensitivity of radio astronomical instruments. If you see this example below, you know that the cosmic rays, the most energetic cosmic rays, they travel, they have an energy of about 10 to 20 electron volts. And when they hit you, it's the same energy as the tennis ball at a speed of 100 kilometers an hour. Small cosmic rays. We're only lucky that they're so small they just go through. You don't get them to do much damage. But you compare it with radio astronomy, and all of the telescopes on Earth, working for 70 years, have collected energy which is smaller than the energy of one single falling snowflakes. So this is the difference between the energies, and that's the challenge of radio astronomy when you're talking about this kind of event. So all of the information that we collected from the universe and all of these wonderful discoveries, they carry with them the energy which is smaller than one falling snowflakes. So the other challenge in astronomy and in radio in particular was the achieving the better angular resolution. Why we need it, you've seen many times this year in the press releases dedicated to the imaging of the event horizon. And if we, this is one of the most fundamental questions in the present day astrophysics, what happens in the scales close to the event horizon. But if we want to solve these questions, you see that if you talk about the size of a black hole in a typical galaxy that we observe at about 1 billion years away, say, is 3 nano-arc seconds. And then when we count all these zeros here, if you want to convert it to a degree. Or 5 micro-arc seconds if we're talking about black hole in our own galaxy, and about 2.5 micro-arc seconds in the M87. So if you want to achieve this kind of resolutions, your interferometry is the only way available for us at the moment to do so. So if you look at that diagram on the right-hand side, you see the resolution of different instruments working in different domains of electromagnetic spectrum, from radio to gamma rays. And you see that radio instruments, they achieve a much better resolution than most of the existing telescopes. And this telescope called Maxim, it's one of the many incarnations of proposed telescope to be working in X-rays and be actually also in interferometry. So with this kind of things, you need to, again, to go to interferometry in order to get the resolution which is sufficient to follow up such an interesting objects like black holes, cosmic black holes. And now, let me just go through some Hall of Fames of VLBI Hall of Fames. It's severely abridged because if you want to give a good account of the VLBI results, you probably need a few days, and that's what usually happens when people from VLBI observatories come together to discuss these new results. So, this is one that you cannot avoid this year. That's the M87. You've seen it about probably 55,000 times by now. This is the new reincarnations. You see that image compared to the size of our solar system, confirming the results of the quiz. So essentially, but it's still, you can see how impressive it is. In a galaxy about 53 million light years away, you can resolve structures which are so much comparable to the solar system. You can see actually Pluto, if Pluto was there and the meeting was bright enough for you to be detected, to detect it. So the resolution, angular resolution, is actually, at the moment, also belongs to radio astronomy, to the Space VLBI mission, Radio Astron, which, as I said before, combines telescopes on the ground with an antenna which can be separated as far as 350,000 kilometers away from the Earth. And that allows this kind of telescope to get an angular resolution of about 20 micro-arc seconds and reaching all the way down to about 10 micro-arc seconds. So if you think what is 10 micro-arc seconds, is 1 cent coin on the moon. And I forgot to mention on that diagram that, again, if you talk about these resolutions, that's what you see. 1 milliarc seconds is a man on the moon. 1 microarc seconds is a child on the sun. And I don't see if you see that in all of the screens, but 1 nanoarc seconds is what you were talking about. It's the football field on Alpha Centauri. So you need to be with 3 nanoarc seconds to detect these black holes or image black holes in the distant galaxies. 1 nanoarc seconds, with 1 nanoarc seconds, you would see football fields on Alpha Centauri. Not quite the score of the game, but still approaching these kind of capabilities. So we do now 10 microarc seconds. It's way away from 1 nanoarc seconds. We probably can reach it, but not anytime soon. But what we can see now is that at this kind of resolution, everything is live. Nothing really is still in the sky. So you look at any source for about 200 days, and you see how much evolution happens there, how much changes there. It's really alive pictures. And not only on the Earth, you can actually, by virtue of providing such a beautiful angular resolution accuracy on the sky, you actually get the same accuracy, or extremely good accuracy, on the positions of the radio telescopes on the Earth. And by doing that, you can actually measure the continental drift. There's all these measurements, not all of them come from VLBI, but a majority and most accurate measurements come from measuring VLBI, observing with VLBI distant quasars. So you not only know things about the quasar, you also know things about the continental drifts on the ground. Another thing, if with astrometric applications of VLBI, you establish the most accurate inertial reference frame, which is extremely important for the space navigations, for the military applications, and for civil applications, such as your typical navigator or your iPhone. Your iPhone uses GPS in order to provide you with the information about the next store, cafe, whatever. But if the GPS was not corrected with the help of the measurements done with radio interferometry, you'll be terribly off within a couple of weeks, because the GPS needs to be corrected continuously in order to provide this information, sufficient accuracy on Earth. So VLBI helps that, and this is one of these tasks that you really do not usually being aware of the usage of such a usage of radio interferometry. Now, as I said, everything is changing with such a resolution, and you can even see the nonlinear effects of the solar motion through the galaxy, which is in a way is an amazing thing. Is that you realize that the sun takes about 225 million years to turn around the galaxy, and we already see this. We can actually see this. You see the vectors here. This is the systematic offsets and positions of the distant quasars measured with VLBI, and you see they form a particular pattern, which which reflects this curvilinear motion of the sun around the galaxy. So we know that, or you can actually sense it in a way with this kind of measurements, the motion of the sun around the galaxy. And finally, as I said, the next generation of interferometers will provide extremely good sensitivity, but not only that, it will also provide extremely good angular resolution. The mission, which is now planned, is going to be put at about 1.5 million kilometers away from the Earth. So the yellow dot here is the sun, the blue one is the moon, is the Earth, and then there's 1.5 billion kilometers away from it is the point where the this telescope millimetron will be placed. So at these separations, you would really approaching the 1 nanorec mark. So with this telescope, would be really able to see or start looking at football fields on Alpha Centauri. Of course, they're not bright enough for us, but what it would be bright enough is the potential investigations of such enigmatic objects as wormholes, which in some theoretical minds connect different parts of the universe together by basically piercing the habitual topology of the three-dimensional space. And in order to observe this kind of wormholes, you really need to get to this 1 nanorec resolution benchmark. So that's how VLBI will continue help us to get the new answers to these and greatest questions of physics and astrophysics. So let me just finish again. This was a long journey for interferometry, starting from 1666. So with this kind of damaging experiments done by Isaac Newton. But you can ask yourself a question, just to think about it. What if they did not allow him to do that? What would have happened with us? What would know about the spectrum of light? What would know about the dispersion? What would know about the other things? And that's a question which we should ask every time we think that the fundamental science does something nonsensical. It may be doing something nonsensical from our point of view. It was totally nonsensical from the point of view of people from the 17th century. But 4 centuries later, you can do wonders with the things that started so long ago. Thank you.
Hello, yes. Thank you for such an interesting talk. It was really very interesting. Any questions? Questions about observations, interferometers? Did you follow the questions? No, nothing? Questions? Come on, people. If you didn't follow anything, you can ask. Please explain the slide 1 again. We have a question here. Yes.
Okay, thank you for that very nice talk. Just a question, you showed these great resolutions and the nano-arc seconds and the milli-arc seconds, and you made this very nice comparisons with what you could see in terms of size. And did anyone ever just try to do some kind of a everyday Joe's experiment just to make an image of, let's say, Pluto or something like that, just to make just to show what is possible nowadays? So I have no idea, but I think it would be impressive to the everyday Joe. Just
yes. The trouble, of course, yes. People trying to do the imaging planets. In fact, there was an example that I wanted to show, and I realized I didn't have time. People use interferometer to image subsurface emission from subsurface of Mercury, 70 centimeters below the surface, because that's where the radio emission comes from in Mercury. You can do that, but if you want to make an image with such a resolution, you need an object which would be bright enough. In other words, hot enough to do so. And thermal objects, they cannot be suitable for that. Most of them cannot, because usually you could do stars, but if you want to achieve a better resolution, the effective temperature is much higher. So you can only use that technology or this technique on objects which are non-thermal in their nature. It's another thing, but basically highly relativistic plasmas, essentially. So that's the limitation. If we can, as I say, I was showing this effective a virtual lens. If we can fill it better, you can actually reduce the temperature, and then you can get this wonderful images at wonderful resolutions of objects which have lower temperatures, even Pluto, for instance. But for that, you need, again, much better quality of our virtual telescopes. That may be SKA, maybe something that Alan was discussing before, but not at the moment.
Right. Thank you. Any other questions? Oh, here.
Andrei, we now know that around the black hole in the galaxy M87, there's bright stuff that you can image with the black hole, focusing it to make a ring around. For a wormhole, what would you expect to see for a wormhole?
There are two things. There may be emission coming from the center because the matter may not only fall inside that wormhole, but also go outside. And another thing, you should see much stronger magnetic field. So maybe 10 orders of magnitude stronger than what you see in around black hole.
Last question. Any last questions from internet? No? No? Last questions? No? Well, then let's thank our speaker one more time. So for the last 10 educational minutes of our event, we actually have a slam talk. So if you were part of our event, the last 2 events before the summer break, we are trying to introduce a new idea, and please give us your comments, let us know how you feel about this. It's a slam talk, it's a 10 minutes or even shorter talk, very to the point, about a very specific topic. And today we will have Hannah Hoffman. She will give the SLAM talk in English. Yes? Hello. We're happy to have you here. And Hannah has been working since 1999 at the United Nations Framework Convention on Climate Change, which is abbreviated in the very simple words of UNFCCC. So, very simple. She is part of the innovation group of the UN Climate Change Secretariat, so very on time, you know. We're doing very well with the news these days. And she organized monthly talks, stand-up talks actually, on innovation aimed at triggering thoughts on climate action. And that's actually what she's going to tell us about today.
Jetzt geht's. Also, ich wollte eigentlich nur kurz noch die Ansage auf Deutsch. Wir haben ja genau das geplant, auch mal ein bisschen außerhalb der Astronomie nach SAM-Talks zu gucken. Und jetzt genau passend zur Klimawoche haben wir also auch einen ganz besonderen Gast eingeladen. Und zwar ist es Hannah Hoffman, die hier einen Science Slam für uns vorbereitet hat. Seit 1999 arbeitet sie für die Klimarahmenkonvention der Vereinten Nationen und ist dort zurzeit in einer führenden Position für die Koordination und Stärkung der Begleitung von Verhandlungsgesprächen zuständig. Sie ist Teil der Arbeitsgruppe für Innovation des UN-Sekretariats für Klimawandel und organisiert monatliche Vorträge, die zum Nachdenken über Lösungen zum Klimawandel anregen sollen. Und damit auch nochmal einen großen Applaus für Hannah Hoffman.
So, hello everybody. I hope everybody can hear and see me. I'm very happy to be here. I'm very honored to be invited. I have 3 challenges. One, I had a little accident over the weekend, so I cannot speak with a lot of impetus, so I hope you can hear me. Secondly, I'm not an astronomer. I'm a parachuter. And thirdly, I'm here as a last speaker. So I hope you can all listen to me and learn a bit how I slam your science. Because today, I'm speaking on behalf of my own capacity. I've been working for a long time in the climate change arena, but today, everything what I'm saying is my own views. So, let's start. Climate crisis. What do you mean? Oh. Well, this afternoon, the Secretary General, in a live audio from New York, said we need to start talking about the climate crisis. And he said we even should not talk anymore about global warming. We should call it global heating. So I'm going to give you some information about the current knowledge and urgency to act. So what would you like to hear? Would you like me to talk from the red pill perspective? Or would you like me to talk from the blue pill perspective? Would you like to feel safe and sound? Or would you like to hear how things are? This is the definition from Wikipedia, and you may recognize it's from Matrix. Now I have 3 questions for you. 1, since when do we know? 2, what do we know? And 3, why don't we act? Excuse me, what do we do now? So since when do we know? Now, when you look at the milestones, you will see that since pretty long a time, we do know. We do know some 100 years about climate change. Here, this is where we will be end of December in Santiago de Chile, where Alan was reporting about. And we will hopefully conclude the chapter of the rulebook of Katowice. So what do we know? We do know a lot about science, about politics, about economics, about media, and about social activities. This may look familiar. It is quite a curve. It is even much more a curve than you've seen beforehand. These are the ppms, the atmospheric CO2 concentration. And it's mounting and mounting and mounting. It is beyond safe levels, and we do know. What else do we know? This is the Keeling Curve, known to many of you, I guess. I have embedded 4 videos in this presentation. So when you get it, you can have a look at the videos. I will not play them now, because it would be too long. So what else do we know? We know, based on 30 years of IPCC research, that climate change is real, that the threats will increase, and that we do have the means to tackle it in a cost-effective manner. We know every little action matters. What do we know on a political front? 197 parties adopted the Climate Change Convention, and we know we need to stabilize greenhouse gases. We also know that we need to accelerate the work. And we know we need to strengthen the global response. And this not only below 2 degrees, but meanwhile well below 1.5 degrees. What we also know is that the whole year of 2019, we have had one activity after the other. And here is the climate summit, which actually took place yesterday. And here is a conference in Chile I was talking about. What we also know is that many actors went to New York to say, we pledge action because we know it is so important, and we want to be climate neutral by 2050. What do we know from the economics? We know that many of the calculations are an underestimate. It's an underestimate, and we run the risk to have damages on a scale larger than the 2 world wars of the last century. What we also know is that middle of this year, we have used up all of our resources in Germany. That means we're now living on a rent. We live as if we have more than one planet. Every day we are living now is no longer what we really have. We're loaning. So I have brought some videos which you can look later. We can also watch one video at the end. It is Al Gore, An Inconvenient Truth. He has told us 10 years ago what it will look like. And many people were laughing about him. Some 10 years later, he made the second video, and he proved that he was right. So what you see here is we know that this is what we can achieve with the current policies. This is what we can achieve with the national determined contributions. But this is what we need to achieve with the help of all of you. This is what civil society has to deliver, because policy alone is not enough, and national contributions are not enough. We know that many actors stand together now. They unite to combat climate change. We know that more than 4 million young people went on the streets. And please have a look at the videos. They're very, very touching. We know there are lots of activities. For example, many more children have gone so far as to plant millions and billions of trees. This is Felix Finkbeiner from close by here. There were many children before Greta trying to change the world. We also know that we need a fast exit and fast solutions because we're running out of time. So people like the Nobel Peace Prize winner Desmond Tutu said, we know since decades, we know all this. There's no apologies. We know we are responsible. So now I'm coming to the third chapter. What are we doing? So what are we doing ourselves, each one of us? What are we doing to walk the talk on climate action? What is our personally determined contribution? We're not looking at the politicians. We're not looking at the UN. We're looking at each one of us. And there is a sculpture. It's called Climate Change Negotiations, I think. So, that's interesting. Anyway, the question is, what do we do now? And the answer of Al Gore, who I met in Paris in 2015, was to say, learn more about climate change. He also said, use your vote to make things happen. He said, let your voice be heard. And he said, passionately argue your case, actively engage your family and friends. And he also said, review your lifestyle, your diet, and your transport. Today, I'm here to tell you about stand-up talks on innovation I'm organizing at my work. And I was so fortunate to have Alan and Eleni there, and also Candide, who's sitting here. And we also have flexible innovation gatherings. And I'm here at the Astronomy on the Tap. And all of these events aim to trigger your thought and your subsequent action towards concrete, measurable implementation at our work, in our cities, at our home. And I would like to invite you to be all part of this solution and bring your friends. Thank you very much. Sorry, I'm here for questions, just in case.
Yeah. Thank you for this talk on a very important, maybe the most important topic that we have now. So, are there any questions to Hannah?
You don't need to worry. If you don't have questions, you're very welcome to contact me. I will leave my contact address here, and please feel free to ask me any questions you want. Auf Deutsch, en français,
Yeah, I can
en
translate.
English, en español, como quieres.
So first of all, thank you for the talk. And my question is, how bad are things going to be and how soon?
Okay, it is not an easy question, right? It depends on your definition, how bad and how soon. Everybody has a very subjective definition. But I can tell you that we are the first generation to live climate change, and we're the last one to change things. And that means that what we have very soon is we have our capitals being 4 degrees warmer. And we have, according to the IPCC report, there were just, I mean, the 1.5 report came out last year, and there's another one on oceans and land, which was just released. And so what it says is that we only have a few years. We have less than a decade to actually do things. And that's the reason why the world leader went to New York, and they made pledges for 2030, and they want all to be carbon neutral by 2050.
All right, one more question maybe?
Thank you for the talk. That was really good. So recently, the world witnessed Amazon fires, to which the president of Brazil, Jair Bolsonaro, he commented that his belief that climate change is not real. So his mere ignorance may cost us like half a billion lives or so living in the nearby areas of Amazon. So how do we actually convince, like how do we get people to convince that yes, it's a real event that is taking place globally, and like make them believe if they are not ready to believe like themselves, like administering the changes?
Yeah, it is not an easy question. As I said, I'm speaking here on behalf of myself, but after all, I'm still an international civil servant. And so we are serving all the countries, and so we will, of course, value all the point of views of the different countries, and we will try to bring them together. That is my job, to support the negotiations and to bring everybody together so everybody can make their views heard and their preferences expressed, and look for win-win situations. So what is very important in what you said is Brazil is a very important actor, not only with regard to the rainforest, but obviously with the fires which are happening, and I know that a lot of countries have offered help. But also the next COP, that's what we call the big conference at the end of the year, which will take place in Chile. The Latin American region, they are all talking to Brazil. So there are lots of countries who are doing a lot of things, such as Costa Rica, where the pre-COP will take place, and they're all talking to Brazil to see in how much one can find a good solution for all of the countries. So that is what I can say, that a lot of discussions are going on, because as you know, one of the outstanding issues for this conference is called Article 6 of the Paris Agreement, and Brazil is a big player in that. So there are lots of intense negotiations going up toward that point, and we're looking very much forward to having a positive response at that point, including action on the ground in Brazil. Thank you.
Okay, and with that, let's thank our speaker again.
Thanks.
So we are here for the last part, which is the prizes, so you should be excited for this. We have Manali today with us, who is our prize master, and she will give first the prizes for, I see blue, so the quizzes. And the way this is going to work, sorry, Kevin, is we are going to call the numbers, or Felix is going to call the numbers, and we ask you, if you win, please come to the stage, we'll give you the prize, and please stay on the stage so we can take a picture with you people. So this is for the quiz, this is blue.
Genau. Ich werde jetzt einfach die Zahlen vorlesen und jeder, der dann diese Zahlen in der Hand hält, einfach auf die Bühne kommen und den Preis entgegennehmen. Und bitte kurz hier bleiben, weil wir wollen gleich noch ein Foto machen. Die erste Zahl. 163. 163.
Sorry, Kevin. 136.
Where's the winner?
Woo! Come over, come over. Oh, sorry. What do they get? Beer glass. Kolsch beer glass. It's true.
Correct.
Correct. Please stay. Join us here in the stage. Number 2.
Let's go deep.
Number 3. Oh, you're right. No, you're right. Yeah, sorry.
113. 113.
130.
13. To be clear.
13. So I don't know my numbers in German. 113. And they get a beautiful Euclid notebook. So you can write all your thoughts about astronomy. Come over. Very good. Next one is for the quizzes, which means it's all the right side.
Die Nummer 177. 177.
177. Very good. Sprechen
Yes.
Sie Deutsch? Yeah, German. So you get a book, eine kurze Geschichte der Zeit. 2 more prizes for the quiz winners.
Die nächste Zahl. Moment. 174. 174.
134. Oh, I see someone. Yes, come over. And she gets a beautiful EOT bottle that you don't see, but believe me, it's beautiful. It's great.
Ja, die ist wirklich schön.
And last but not least is actually the price of a Kino-Gutschein. Thank you, Fiddlers. Sponsored by Fiddlers. And the lucky one is
145. 145.
145.
You're a lucky winner.
Woo! We have a lucky winner. We are going to take a very quick picture, and then you guys can go ahead. Ta-da! Come here. We're going to take a very quick picture. Join us. 1, 2, 3. Very good. So now we're going to go for the winners of the donations and the pint glasses.
Nochmal Glückwunsch an die Gewinner vom Quiz.
We have 7 winners, and the winner actually of the pint glasses, so what you voted the most for was the Hubble Space Telescope. So apparently all telescopes is your thing.
Das gute alte Hubble-Teleskop.
Ja. Na, ik mag die neue. So lucky hand of Felix is gonna pick the number 7 winner.
76. 76.
76. 76? Yeah?
76.
76.
76.
Oh yeah, we have a winner.
Ah. Ja, richtig.
And you get IFA mug, Argelander Institute for Astronomy mug. Yes, that's where I work, so it's good. The next winner will actually get a ruler from ESO, European Southern Observatory.
Und zwar geht das an die 58. 58.
58. Do we see a 58? The right side again. And you get a beautiful ruler that shows you a supernova. I believe. No, that looks like a galaxy.
Und noch
Gas.
eine. Okay.
Nächste.
Die 71. 71.
71. We have no bias towards the right. It just happened.
Ja.
And
Das ist
I
alles
hope you like
Zufall.
Kolsch because you get a Kolsch glass with astronomical units.
Ich versuche jetzt mal was für die andere Seite zu ziehen.
Yeah, hopefully.
Vielleicht muss ich noch ein bisschen tiefer graben.
Are you right-handed? Is that why you're choosing all the right-hand people?
I am,
The right
but-
side.
I am, but... Oh, this is simple. 1. 1.
Eins. Eins. Oh, we have a win. At least it's the middle. And you can also write your thoughts in a beautiful Euclid notebook. Yes. We have 4, so we have 3 more to go. And the next person will get 100 things to see in the night sky.
Und
From
zwar, für die,
planets to satellites.
und zwar für die Nummer 91. 91.
91. 91. Oh, that's left. That's left. Very good. Yep, 91.
So, noch 2 mehr glückliche Gewinner.
2 mehr, genau.
Äh,
The lucky hand.
79. 79.
Apparently the right side was the correct side today.
Or the lucky side.
What did you guys do on the left? What happened? And I hope you don't have an AOT bottle because you are getting an AOT bottle. Yes, that's the correct answer. Okay, last but not least, again, you get a voucher actually for the Kinopolis in Bad Godesberg. They don't pay us for this, believe me. I wish, but no.
Jetzt mal gut durchmischen.
It's gonna happen. Du-du-du-dun.
Es ist das, was ich in der Hand halte. 31. 31.
31. Please tell me it's the left. No? Oh, well, yes, you count as the left. I'm glad. Good shine. Yes, very nice. 3 seconds, we're going to take a picture. This makes it the fastest. We have Toma, who's our cameraman. Yes. In the meantime, thank you, Toma. Thank you, guys. Congratulations.
Glückwunsch an alle Gewinner.
Okay, this brings us to the end of the event. We are really trying hard to make it in the 2 hours, which we are obviously past, but we only passed that time by 10 minutes, so we're doing okay.
Okay, damit sind wir jetzt auch schon fast am Ende angekommen. Also, ich möchte mich nochmal bedanken bei allen, die hergekommen sind. Glückwunsch an alle Gewinner und ich hoffe, ihr hattet hier so viel Spaß wie wir heute. Und Astronomy on Tap immer jeden Dienstag, jeden letzten Dienstag im Monat. Und wir sind auch auf allen Social Media unterwegs, also bitte auch folgt uns da und abonniert uns auch gerne auf YouTube.
Follow us in all social media, all those things, Twitter, Instagram. Thank you so much for being here. I don't know what I'm supposed to, it happens the last Tuesday of every month. 2 quick things. Subscribe, and Kevin will play the drums after, and then Felix will go for a moment. Go ahead. Oh, yes. And the next speakers for next month will be Florian Pacot talking about Chandra and X-rays in space. And Professor Thomas Reiprich also talking about X-rays in space, but a new mission. Very exciting.
Okay, wir freuen uns auch, euch alle dann wieder zu sehen, und zwar im Oktober, wenn wir wieder da sind. Und dann wird Dr. Florian Pacot und Professor Dr. Thomas Reiprich passend zum, für X-Rays, zum X-Ray-Spezial, also für Röntgenstrahlung wegen dem Jubiläum, Vorträge halten. Also ihr seid herzlich willkommen, auch dazu so Astronomy on Tap zu kommen im Oktober. Und damit gute Nacht.
Ja, vielen Dank.